Understanding Aging Through Computational Modeling. This summary was created by Speechify, based on the new paper by Léo Pio-Lopez, Benedikt Hartl, and Michael Levin. The core theme of this research is that aging can be conceptualized as a loss of goal-directedness within multicellular systems, with significant implications for regenerative medicine. Introduction to aging theories. Aging is a complex biological process characterized by a gradual decline in physiological functions, leading to increased vulnerability to diseases and ultimately death. Traditional theories of aging can be categorized into two main groups: damage-based theories and programmatic theories. Damage-based theories suggest that aging results from the accumulation of cellular damage over time, affecting critical components such as DNA, proteins, and cellular structures. In contrast, programmatic theories propose that aging is genetically predetermined, encoded within the organism's genome. Recent research, however, has begun to explore a new perspective. This perspective posits that aging is not merely a consequence of damage or genetic programming, but rather a result of proto-cognitive dysfunction in cellular collectives. This implies that once developmental goals are achieved, the cells lose their directionality and thus begin to degrade. This innovative viewpoint suggests that aging may arise from intrinsic dynamics within complex biological systems that lack ongoing goals. The role of neural cellular automata. To investigate this hypothesis, researchers employed neural cellular automata, NCAs, a computational model that simulates multi-scale homeostatic morphogenesis. NCAs consist of a grid of cells that interact locally, making decisions based on their immediate environment. This model allows for the exploration of how cellular agents can self-organize to achieve specific morphological targets. The findings from simulations using NCAs indicate that 1. Aging emergence. Aging occurs naturally after developmental milestones are reached, highlighting the absence of evolved regenerative goals. 2. Acceleration factors. While factors such as cellular misdifferentiation and genetic damage can accelerate aging, they are not the primary causes. 3. Information dynamics. Aging correlates with increased active information storage and transfer. Entropy. While spatial entropy reflects structural loss and accumulated noise. 4. Memory of lost structures. Despite organ loss, spatial information persists, suggesting a memory of lost structures that can be reactivated for organ restoration. 5. Efficient restoration strategies. Targeted regenerative information that includes patterns of affected cells and their neighbors enhances rejuvenation efforts. Insights into information dynamics. The research emphasizes the importance of information dynamics in understanding aging. By applying information theoretic metrics such as active information storage (AIs) and transfer entropy (TA), the study uncovers how aging processes are governed by the cellular information processing capabilities. Active information storage (AIs) quantifies how much information from past states is relevant for predicting future states, indicating a system's ability to retain and utilize historical data. Transfer entropy (TE) measures the directional flow of information between cells, revealing how interactions change as aging progresses. Spatial entropy (SE) assesses the randomness of cellular states, providing insight into the structural integrity of tissues over time. These metrics collectively illustrate how aging is not merely a passive decline but involves complex interactions and information processing at the cellular level. Cellular competency and aging. The study identifies several mechanisms that contribute to the aging process, specifically focusing on cellular competency. These mechanisms include cellular differentiation. The reliability of cell differentiation is crucial. An increase in noise during the decision-making processes can lead to misdifferentiated cells, which negatively impacts tissue integrity. Decision-making reliability. The ability of cells to make reliable decisions is essential for maintaining tissue function. Decreased reliability in decision-making can accelerate aging. Cell-cell communication. Effective communication between cells is vital for coordinated responses to environmental changes. Disruption in communication pathways can lead to aging-related decline. Genetic damage. Accumulation of genetic mutations can impair cellular functions, contributing to the aging process. By understanding these mechanisms, researchers can identify potential intervention points for rejuvenation and longevity. Regeneration as a therapeutic approach. One of the most promising findings of the study is the potential for regeneration to counteract aging. The research indicates that even after the loss of organs, the underlying information about those structures can persist, providing a basis for restoration. Key strategies for regeneration. 1. Targeted interventions. Restoration efforts can be optimized by focusing on specific cells that have deviated from their target states rather than resetting entire organs. This approach minimizes disruption and enhances the efficacy of rejuvenation. 2. Boundary considerations, including surrounding tissue in regeneration strategies, can significantly improve outcomes. The interactions between affected organs and their neighboring cells are crucial for successful restoration. 3. Memory retention. The concept of morphological memory suggests that tissues retain information about their past configurations, which can be leveraged for regenerative therapies. 4. Dynamic interventions, implementing targeted interventions that reactivate dormant regenerative pathways can effectively rejuvenate aging tissues. Implications for future research. The findings from this research offer a roadmap for future studies in aging and regenerative medicine. By integrating computational modeling with experimental biology, researchers can explore new therapeutic strategies that modulate aging processes and enhance recovery from injuries. Potential research directions. Investigating indeterminate growth. Further studies could explore how organisms with continuous growth exhibit minimal aging, potentially revealing insights into effective anti-aging strategies. Understanding morphogenetic goals. Research should focus on how to provide new morphogenetic goals to aging tissues, potentially reversing the aging process. Exploring bioelectric patterns. Investigating the role of bioelectric signals in maintaining tissue integrity could lead to breakthroughs in regenerative medicine. Examining heterogeneity in cellular responses. Future studies could analyze the effects of allowing cell-specific functional mutations, providing insights into the implications of cellular diversity in aging. Conclusion. In summary, the research presents a compelling case for viewing aging as a loss of goal-directedness within multicellular systems. By utilizing neural cellular automata to model aging dynamics, the study reveals critical insights into the mechanisms underlying aging and the potential for regeneration. The findings suggest that reactivating developmental pathways may offer a viable strategy for rejuvenation, paving the way for innovative approaches in regenerative medicine. This research not only enhances our understanding of aging, but also opens new avenues for therapeutic interventions that could transform the treatment of age-related diseases.